Hello, my name is Alexander, and today I'll be teaching you a little bit about the number systems you will find in AQA GCSE Computer Science, and then we'll take a bit of a deeper look into one of them. There are three number systems you'll need to know for your exam: the binary number system, the decimal number system, and the hexadecimal number system. In this video, you can expect to learn about the number systems you will encounter in AQA GCSE Computer Science, how to convert between these number systems, the kind of arithmetic you will be doing in a exam paper, and we'll look through some of those exam papers and the questions you'd expect to find in them. On screen, you can see the parts of the specification that this video will cover. So let's start with the number system that you've been using your entire life and in those painful GCSE maths lessons. The decimal number system gets its name from the Latin word decimus, meaning tenth. As you can probably guess, the decimal system has digits with 10 possible values, from 0 to 9. And each digit contains a value 10 times larger than the last. That is to say that the hundreds column is 10 times larger than the tens column, and the tens column is 10 times larger than the unit column, and so on. The decimal system is very intuitive for humans to use, perhaps because we have 10 fingers, which makes it easier to count, especially when you're young. Now see, the decimal system is not very efficient for computers. 10 possible choices for every single digit gets very confusing very quickly, especially for the electronics inside. Instead, computers work in the binary number system. If you've ever seen words like bi-weekly or bicycle, you can probably guess that binary is for two number systems. That is to say that you have two choices, 0 or 1. Since there are two possible values per digit, the numbers multiply by 2 with every digit, rather than 10, like in the decimal system. That is to say that 100 is twice as big as 010, which is twice as big as 001. Naturally, powers of 2 are much less intuitive for people to use. And part of that is just because you don't end up with very nice round numbers. For example, the 8th digit in the binary number system is 128, if the value is set to 1, which is very confusing. On top of being unintuitive though, binary numbers are just extremely long compared to their decimal counterparts. For example, 255 is represented as 11111111. That's 8 digits instead of 3. To work out the maximum value of an n-digit binary number, simply use the formula on screen, that is, 2 to the n minus 1. Alternatively, you can find the value of the leftmost digit in an 8-bit number, that is 128, and then multiply by 2 and subtract by 1. As you can see on screen, we often refer to a singular digit of a binary number as a bit, particularly in the context of computers. Now, a collection of 8 bits is known as a byte. As we've already established, binary is the number system used in computers because it's very simple to design electronics that work around ones and zeros, or yeses and nos. Now, bytes, that is 8 bits, also have SI units like a lot of the things you'll discover in GCSE physics. So, 1 kilobyte is 1000 bytes, 1 megabyte is 1000 kilobytes, which is 1 million bytes, and so on. Now, we use the capital B for representing bytes, and we use the lowercase b for representing bits. And a very interesting tidbit that you don't need to know for your exam is that at one stage we used to use powers of 2 for the SI units. That is to say that 1 kilobyte used to be 1024 bytes. Now, those units are referred to as kibibytes, or mebibytes, or gebibytes, which again you will not need to know for the exam, but it might be useful for you. So, binary is too long to work with for human beings, especially with very large numbers in the tens of thousands or millions. As you saw in the last few slides, just 65,000 takes a whopping 16 digits. So what if there was a number system that's directly related to binary, but much more concise, even more concise than decimal? Hexadecimal. So, as you can probably tell from the name, you have hexa, meaning 6, decimal, meaning 10. Combine them together, you have a number system with 16 possible choices. That is to say, you have 0 to 9, and then, unfortunately, A to F. Now, each digit in hexadecimal is 16 times larger than the last. Just like how each digit in decimal is 10 times larger than the last, and each digit in binary is 2 times larger than the last. That means that the second digit you have to multiply by 16, the third digit you'd have to multiply by 256, and so on. Fortunately, in the exam, you'll only ever be dealing with hexadecimal numbers that go up to 255, so it'll only ever be 2-digit hexadecimal numbers. And an interesting tidbit with hexadecimal is the fact that because it's 16, which is the power of 2, you can actually represent it perfectly with a binary number. That is, 16 can be represented with 4 bits. As an aside, if you've ever worked with HTML or used an image editor such as Photoshop or GIMP, you've probably seen colors represented using hexadecimal values, such as hashtag FFFFFF being a representation of pure white. An important skill you'll need for computer science is to be able to convert between these three number systems. It's very important to note that for your exam, you will never be converting numbers that are higher than the decimal value of 255. That is to say, in binary, the highest number you'll ever deal with is 11111111, and the highest hexadecimal value you will encounter is FF. In these examples, we will be using the number 155 to demonstrate the conversions. So, to convert between decimal and binary, begin by drawing a 2 tall, 8 wide table. From right to left, fill in the top row with the powers of 2, starting with 2 to the 0 or 1. And now we're going to fill in the bottom row piece by piece. You want to go from column to column, finding the largest power of 2 that you can subtract from your number. In this case, with 155, that is 128. You subtract that and put a 1 in the column. So we're left with 27 now. So the next biggest number we can subtract from that would be 16. So we subtract 16, we end up with 11. And we put a 1 in the 16 column. Then we put a 1 in the 8, and the 2 in the 1 column because we can subtract, as you can see on screen. And then fill in zeros for everything that we did not put a 1 in. Now you have a 8-digit binary number that represents the decimal number. In this case, the binary number would be 10011011. Now to convert from binary to decimal, we're going to need that 2x8 table again. Just like before, you're going to want to fill in the top row of the powers of 2, starting from 2 to the 0, and on the bottom row you're going to fill in the binary number. Now, what you will be doing is you'll go from column to column, and every column that has a 1 in the binary number row, you're going to add the power of 2 to a running total. So, in this case, we have 128, we have 16, we have 8, we have 2, and we have 1. Now, we just have to add these together to get our final number, which is 155. Now, since we're only going to be working with 2-digit hexadecimal values, we're going to use a cheat strat. To obtain the leftmost digit of a hexadecimal value in this case, you will want to divide your original number by 16. So in this case, 155 divided by 16 is 9, and we're left with a remainder of 11. See, that remainder is actually our rightmost digit. Obviously, 11 isn't a hexadecimal value, so you're going to want to convert that, which will convert to B. Now we just have to combine these together and we get 9b, and that is our hexadecimal value. Converting from hexadecimal to decimal is similarly easy. Start off with your hexadecimal value, 9b, and now split each digit from the other and convert it to its decimal equivalent. So 9 is fine, and b we convert to 11. Now all you have to do is multiply the left digit by 16, 9 times 16 is 144, and add that to your rightmost digit, which is 11, and together we get 155. Now, as you mentioned before, one hexadecimal digit is equivalent to 4 bits. So, what we can do is we can split a binary number into sets of 4 bits, and then we convert each of those into the decimal equivalents. So, 1001 is equal to 8 plus 1, or 9, and 1011 is equal to 8 plus 2 plus 1, or 11. So now we have two numbers, 9 and 11, and we just convert them when necessary to hexadecimal. So 9 is fine as is, and 11 turns into B. And that is literally all you have to do. For some of you, it might now seem obvious how to convert from hexadecimal to binary, but we're going to cover it regardless. So first, let's split our hexadecimal number into its individual digits, 9 and b. And now let's convert those to decimal, 9 and 11. And then the next step is just to convert those numbers into their binary equivalents, 9 being 8 plus 1, or 1, 0, 0, 1, and 11 being 8 plus 2 plus 1, which is 1, 0, 1, 1. So now we have two 4-bit patterns, and we're just going to combine them together to get our final number, which is 1, 0, 0, 1, 1, 0, 1, 1. It's important to note that binary addition is fundamentally the same process as decimal addition that you've been doing your entire life. It's just that your digits are slightly different. The difficulty comes from the fact that the columns increase by factors of 2 instead of by factors of 10. You may be tempted to convert binary numbers to decimal and add them that way, but you will not get marks in an exam for doing so. You might, however, find it beneficial to do so as a way of checking your answer. So we'll begin by adding together two binary numbers. Suppose we have two numbers, 0, 1, 0, 0, 1, 1, 0, 1, and 1, 0, 0, 0, 1, 0, 0, 1. So we'll start off by adding together the rightmost digit, which is 1 plus 1 is equal to 2. The maximum value, obviously, with binary is 1, so what we do is we write down the number 0 and have a carry, just like you would do if you went over 10 in a regular decimal addition. So our first digit is 0. Now our second digit is 0 plus 0 plus the carry, which is 1. So we just write 1 in the column. The third digit is 1 plus 0 plus 0, and since there's no need for a carry or anything, we just write down 1. For the fourth digit, we have 1 plus 1 with no carry, which is equal to 2, which again, we will write down as 0 and add a carry to the next column. Therefore, the next column, the fifth column, is 0 plus 0 with a carry, which we write down as 1. The sixth column is 0 plus 0 with no carry, so we just write down as 0. The seventh column is 1 plus 0 without a carry, so we just have to write 1. And likewise, the eighth column is 0 plus 1 without a carry, so we just have to write 1. So in the end, we end up with the number 1101, 0110, which is 214 in decimal. Now for adding three binary numbers, it's essentially the same process. The difference is now that you have three numbers in a column, regardless of whether you have a carry or not. Fortunately, you'll never encounter a situation where you have 1 plus 1 plus 1 and a carry, which would be equal to 4. Suppose we want to add three numbers, the first two numbers from before, and now a third number, 000110001. So for the first digit, we do 1 plus 1 plus 1, we get the number 3. We subtract 2, which represents the carry, and we write down 1 in the column because that's what we have left. So digit 2 is now 0 plus 0 plus 0 with a carry, so we write 1 in that digit. Digit 3 is 1 plus 0 plus 0 with no carry, so we write 1. The fourth digit is 1 plus 1 plus 1 without a carry, which is equal to 3. Which again, we subtract 2 for the carry bit, and then we write the number 1, because that's what we have left. Therefore, digit 5 is now 0 plus 0 plus 1 with a carry, which is equal to 2, which you write down as a 0 and add a carry digit to the next column. The sixth digit is 0 plus 0 plus 0, but we have a carry, so the answer is 1. Digit 7 is equal to 1 plus 0 plus 0, and does not have a carry, so we just write the number 1. And lastly, the eighth digit is equal to 0 plus 1 plus 0 with no carry, so we write down 1. So in the end, our final number will be 11101111, or 239 in decimal. We've talked about how binary is simpler and faster for computers, and one particularly big reason for this is a process known as bit shifting. As the name implies, bit shifting is when you shift the bits of a binary number in one direction to manipulate the value. See, imagine if you wanted to shift a decimal number like 20 one digit to the left. You would end up with 200. The numbers multiplied by 10. However, if you wanted to shift it right, you would end up with 2. The numbers are divided by 10. Likewise, you can do the same with binary. If you shift a binary number 1 digit to the left, the number is multiplied by 2, and if you shift it to the right, the number is halved. Now, an interesting property with this is that if you have an 8-bit number and you shift it to the left, you will cut off any digits that go beyond the 8 bits. Likewise, if you shift a number to the right, you'll cut off the numbers from the right. So if you wanted to divide 13 by 2, you would end up with 6 and not 6.5. It is worth noting that in your A-levels, if you take A-level computer science, there are fractional representations of numbers. Remember that the binary representation of the number of 155 is 1001, 1011. If you shifted that number to the left, you would end up with 0011, 0110. And that number is actually 54, not 310 like you might expect because of what I just mentioned. So if you were to shift it to the right, you would end up with 0100, 1101, or 77, which if you were to double is 154, not 155. Remember that if you're doing a binary shift, you have to add the zeros on either end. This marks the end of the content coverage. From this point onwards, we are going to be looking at past paper questions and walking through them. I recommend that you pause the video before I answer the questions so that you have some chances to attempt them yourself and identify areas that you might want more practice in. Now let's begin with question 1.1. Convert the binary number 11010100 into decimal. As was shown in the slides, draw out a table that is 2 tall and 8 long. Fill in the bottom row with the binary number and the top row of the powers of 2. If a column has a 1 in it, add the power of 2 from the top row, and if it's a 0, ignore it. So you should end up with a running total of 128 plus 64 plus 16 plus 4, which you add together to get 212. For question 1.2, you're asked to convert 10111,001 into hexadecimal. Now, you should be using the strategy I taught you before, which is to break down the binary number into 4-bit parts, which is to say you should end up with 1011 and 1001. Now, you should convert each of these 4-bit patterns into decimal first. So 1011 is equal to 8 plus 2 plus 1, or 11. And 1001 is equal to 8 plus 1, or 9. Now you're going to need to convert these to hexadecimal. 11 is equal to B, as we've discussed previously, and 9 you can keep as is. Therefore, the answer to this question is B9. Question 1.3. State the largest decimal number that can be represented using 6 bits. To answer this question, we just need to use the formula I mentioned earlier, which is 2 to the n minus 1, where n is the number of bits, or digits. So, the maximum number that can be represented using 6 bits is equal to 2 to the 6 minus 1, or 64 minus 1, which is 63. Question 2.1. Add together the following 3 binary numbers and give your answer in binary. For the first digit, perform 0 plus 0 plus 1, which is 1. For the second digit, write 1 plus 1 plus 0, which is equal to 2, so we write down 0 and add a carry bit to the next column. For digit 3, we have 1 plus 0 plus 0 plus the carry, which is equal to 2, so we write 0 and add a carry to the next digit. For the fourth digit, we write 0 plus 0 plus 0 plus the carry, which is equal to 1. For the fifth digit, we write 1 plus 1, 0, which is equal to 2, so we write 0 and add a carry bit to the next digit. For the sixth digit, we have 1 plus 0 plus 1 plus the carry bit, which is equal to 3. So what we do is we subtract 2 to get 1, write that down in the column, and then add the carry to the next column along. That means the seventh digit is equal to 0 plus 0 plus 0 plus the carry bit, which is equal to 1. And finally, the 8th digit is equal to 0 plus 1 plus 0, so we write down a 1. Therefore, your answer should be 11101001. Please remember not to answer these questions in decimal or by converting to decimal, but again, I do recommend checking your answer by doing so. Question 2.2. Apply a binary shift 3 places to the right on the bit pattern 1010100. Give the result using 8 bits. For this, we just need to get rid of the 3 digits from the right, which are the 3 zeros. So you should have 10101. Write that in from right to left, and then fill in the leftmost columns with zeros, as they do not have any values. Question 2.3. The arithmetic effect of applying a left shift of 2 to a binary number is to multiply that number by 4. So state the arithmetic effect of applying a left shift of 4 to a binary number. Since you know that shifting once multiplies by 2, and they tell us that shifting by 2 multiplies by 4, you should be able to gather that shifting by 4 multiplies by 16. Question 2.4. State the arithmetic effect of applying a left shift of 3 followed by a right shift of 5 to a binary number. As we know, every shift multiplies or divides a number by 2. Shifting left by 3 multiplies a number by 8, and applying a right binary shift of 5 is equal to dividing by 32. From this you know that the number has to have been multiplied by 8 and then divided by 32, which is simply written as being divided by 4. Now we're going to look at the sample paper for 2022 rather than the 2022 exam paper. Question 1 of the sample paper begins by showing us a bit pattern 01001110. Question 1.1 asks you to convert this binary pattern into decimal. So, as we discussed in the past, draw out a 8x2 table with the top row being your powers of 2, starting from 2 to the 0 or 1, and your bottom row being your binary number. For every column that has a 1 in it in the binary row, you'll want to add the power of 2 on the top. In this case, we end up with 64, 8, 4, and 2, which we add together to get 78. Question 1.2 then asks us to convert this same number into hexadecimal. We can simply do this by breaking the number down into bit patterns of 4 digits, which we get as 0100 and 1110. 0100 is equal to 4, and since this is a hexadecimal value, don't need to touch it. 1110 is equal to 8 plus 4 plus 2, which is 14, and the hexadecimal value for 14 is E. Now you just have to combine these numbers together to get your hexadecimal number, which is 4E. Question 1.3. A student's answer to the question, why is hexadecimal often used instead of binary, is shown below. Because it uses fewer digits, it'll take up less space in a computer's memory. Explain why the student's answer is incorrect. Now, hopefully you've already kind of guessed that in a computer, all numbers are represented the same way. Whether that's decimal or hexadecimal or binary, they're all represented with 1s and 0s, or binary. And you should know that one hexadecimal number is equal to 4 bits. Therefore, you should answer with something like, one hexadecimal digit is represented by 4 bits in a computer, and therefore hexadecimal must take up the same amount of space as binary in a computer's memory. Question 1.4. Explain how a binary number can be multiplied by 8 by shifting bits. Recall that shifting left multiplies a number by 2 for every digit you shift left. Therefore, shifting 3 digits to the left will multiply by 8. So in this video, we've covered the following topics: an introduction into the binary, decimal, and hexadecimal number systems, converting between these number systems, the fundamental units of binary used within computers, such as bits and bytes, the SI units for bytes, kilobytes, megabytes, and so on, binary addition for 2 numbers, binary addition for 3 binary numbers, and binary shifting in left and right directions. We've also looked at and gone through a few exam paper questions on these topics. Thank you very much for watching this video. I hope you found it informative and helpful in your computer science studies. Now, I recommend that you come back to this video in a few weeks' time as a form of review, just to keep the information fresh in your memory.